Hello there. I'm Ojas Kalra, and I'm making this video to serve as an explanation and introduction to a tool commonly used in game AI architecture, finite state machines. Let's start by getting some basic definitions out of the way first. In a nutshell, game AI architecture is a system that lays down the rules for NPC behavior in a video game. Now, with that in mind, what is a finite state machine? Well, a state machine is a computation model that consists of a number of states. What's a state? A state in this context is a distinct mode or method of behavior for a given entity, defining its rules and actions, what it can and cannot do. And what's a finite state machine? A finite state machine, or FSM, is a state machine with a finite number of states, where the states transition into each other based on set conditions. A really basic and intuitive example of a finite state machine is a traffic light. Now, a traffic light has three states. We'll call these red, yellow, and green. In the red state, the behavior defined is that the traffic light should be red colored and it must stop traffic. It transitions to the green state, and the transition condition is a simple timer. The green state then lets traffic move. It transitions into the yellow state after another set timer, and then the yellow state prepares to stop traffic, which transitions into the red state after a set timer. Therefore, the loop completes. Now, how do we use this in game design? Well, a simple example would be an enemy AI. A basic 4-state enemy AI would look something like this. Now, we're going to cover this specific AI in more detail later in the video, but you can already sort of get the gist of how it may function at a glance. Now, why should we use FSMs in game design? Well, there's a bunch of reasons, but here are the core 4. First and foremost, they're much easier to debug than regular code. If your enemy isn't chasing you when it's supposed to, or if it's chasing you for too long, you know that something's gone wrong in the chase state. That narrows down your search area for a bug a lot more than something like saying the enemy just isn't moving right for some reason. The next thing is clear visual representation. In this example, you can already sort of see how an enemy defined on this state machine may function. It's intuitive and it's clear to someone who might not be a programmer. So designers can see and understand NPC behaviors at a glance. And at any instance, you know the AI's current state and how it's supposed to be performing. The next thing is that they're predictable and controllable. Now, this could be seen as a bad thing in certain scenarios, but it's actually a good thing for us right now because even in complex projects, there won't ever be conflicting behaviors due to accidental interactions. If a state transition isn't hard-coded by you, it won't ever occur. And players can learn the patterns of state machines intuitively and adapt to them. It rewards observant gameplay. The last thing is that they're really customizable. You can sync up animations to state, making animation blending easier, and you can tweak individual aspects and behaviors of each state without affecting any of the others. Here's some more examples of how we could use state machines for non-enemy AI. And with that, let's move on to a demonstration. Here, we've got this capsule as our player. On the top left of the screen, you can see the inputs I'm pressing, and on the top right, you can see the player's current state. Each state is linked to the capsule's color, and the idle state is basic white. Let's take a look at the rest. On a basic left and right input, we see the current state change to walking, and the sprite turns green. How about we try running? When we press shift along with the left and right input, we transition into the running state, and the sprite turns yellow. Next, let's try jumping. When the jump input is given, we see the sprite turn cyan and then red. This is because this code has jumping and falling as separate states. So, while we're moving upwards, we're still in the jump state. However, when our height peaks and the Y movement becomes downwards, we meet the condition for the falling state, and the player turns red. This little snippet of code is what defines our FSM. It uses the player's characteristics to determine its current state, which is then linked to an animator script that then plays the relevant animation in Unity. However, this is a finite state machine coded for the specific purpose of animation. Let's take a look at how we can use an FSM to program the enemy AI we saw earlier. Back in our scene, we have this little square acting as our enemy. It's coded with 5 states: idle, patrolling, chasing, attacking, and dead. As with the player, each state is linked to a color for demonstration. Right now, the enemy is in its patrolling state. The behavior here includes just moving back and forth on a set distance. That circle we see around it is its detection radius. Let's try moving into it. As soon as we enter the radius, the enemy's state changes to chasing and it turns yellow. In this state, the enemy picks up some speed and chases the player, trying to get an attacking range. Once it's close enough, the state turns to attacking, and the enemy turns red. In a proper project, this is where you would program the enemy to use an attack and deal damage to the player. Now let's try running away. When we exit the radius, the enemy loses sight of us and transitions to the idle state. In this state, the enemy is
green,
and it just sits and waits. If we re-enter the radius, it'll start chasing us again, transitioning back to the chase state. Now, in a regular game, you'd be able to strike back against the enemy. But for the purpose of this demonstration, let's just boop. The enemy is now in its dead state. This is what we call a terminal or end state. It's a state that has no transitions, which means that once it's reached, the FSM has done its job and it's no longer required. Let's take a look at the code that makes this work. We start by defining an enumeration containing the states. An enumeration is a fixed set of named constants, each of which, in this case, corresponds to one of our states. Next, we implement each state as its own unique method. The idle state is blank because it doesn't really have any special behavior, and we use onTriggerState to look for the player. The patrolling state does have unique behavior. It moves the enemy back and forth along patrol distance. This is the method. All it does is, if the game object entering the trigger is tagged as a player, and if the current state is either idle or patrolling, it transitions to the chasing state. The chasing state defines the behavior for approaching the player. It contains two if statements that act as our conditions for transitioning to other states. If the player moves too far away and exits the enemy's sightlines, then we transition to the idle state because the enemy can't chase the player anymore. But if the enemy moves close enough and gets to the attack range, then we can safely attack the player and transition to the attacking state. Now, in this demo code, the attack state doesn't really contain anything except for the check to see if the player is too far away and needs to be chased down again. However, in a regular project, this is where you'd have the attack method to have the enemy pick an attack and damage the player. Next, we have the dead state. The dead state is where you'd call the destroy method along with any other specialized death behaviors like spawning a secondary enemy or dropping an item. Next, we come to the transition to state method. This is what lets us switch between states using a case switch. This statement simply tells Unity which code block to run based on a given case. In our demo, this is what changes the color of the enemy. In a complete implementation, you could use this to set values for an animator component. One key thing here is that none of the state methods contain a transition to our death state. This is because the death state is a global state. That is, it can be transitioned to from any of the states. Therefore, we keep the death check all the way up here in our update method. Lastly, again in the update method, we have a second case switch. Why do we need two? Because each serves a different purpose. The case switch in transition to state only runs one time when we move from one state to another. Its job is to handle things that will only happen when we enter a new state. The case switch in update, on the other hand, is called every frame. It's what calls all these methods that we've discussed below. And now that we've seen an FSM in action, let's check out some alternatives. Now, we're going to discuss four major alternatives in increasing order of complexity. The first thing is behavior trees. A behavior tree is a hierarchical structure of nodes, with each node representing our action or conditions, similar to a state in a state machine. It starts from the root over here and goes down to leaves, which are these things. It differs from FSMs by being more modular, and it's better for complex hierarchical making instead of being like discrete states like finite state machines. It's easier to interrupt and blend behaviors together. The next thing is utility AI. Utility AI is a score-based system. So each action has a function assigned to it that's defined by you, and the AI chooses the highest scoring action. It's good for dynamic snap behaviors, and it differs from FSMs by having no explicit states present in it. It's more continuous, more emergent, and less predictable. The next thing is GOAP, or Goal-Oriented Action Programming. Goals here in GOAP are manually set. And you have a open field of actions, such as these. You define a starting state and an end state, and the AI uses pathfinding algorithms to get from the starting state to that end state. You're not assigning transition conditions here, the AI finds them itself. So it's more dynamic and it's more autonomous. So it's less predictable as a behavior, and it's better to have varied behaviors in enemies based on the context. The last thing is a neural network. This is a machine learning implementation of AI architecture, and the network learns from training data. It's capable of producing the most complex behaviors so far. It's used in driving AI in Forza games. This has learned behavior versus the pre-programmed behaviors we've got in other states. And instead of being transparent, there's a black box between them, which we don't know what goes on in there. It's more adaptive, it's the least predictable because entirely new behaviors can emerge, but it's also by far the hardest to debug. In conclusion, these are the key takeaways I believe you should have from this video. First and foremost, FSMs are not the only option, nor are they a perfect mechanism. All the other architectures discussed in this video are valid and have their own pros and cons, and you should use every tool in your arsenal in accordance with your project's needs. Secondly, FSMs work on the grand scale. They're great at simple modular design, but they don't have room for too much complexity. Thirdly, though, this simplicity is a strength. There's any number of uses for an FSM that weren't discussed in this video, and you can adapt one to your needs however you want. And lastly, as a bit of an afterthought, since only one state is active at a time and all transitions and behaviors are pre-coded, it really doesn't take a lot of processing power to run a finite state machine. I hope this video leaves you with a better understanding of AI architecture and finite state machines, and thank you for watching.